Hello everyone and welcome to St. Andrews Institute of Technology and Management. St. Andrews Institute of Technology and Management is the best college in northern India and very good college in entire India. It provides the best education, the best placement in the industry. It's the best in each and every essence. St. Andrews Institute of Technology and Management is the best choice that you can make for your child's future. The subject is Principles of Operating System PCC CSE 206G. The topic we shall be covering are process definition, process relationship, different states of a process state transitions. This is in accordance with the new G scheme syllabus of MD University, Rohtak. I, Shalini, from CSE department, shall take you forward. Process. Now, what is a process? A process is a program in execution. A process is not as same as program code, but a lot more than it. So it is more than program, just more than code. A process is an active entity as opposed to program, which is considered to be a passive entity, right? Process is active wherein your program is passive. Attributes held by process includes hardware state, memory, CPU, etc. That is, it has some system requirements. Okay, to put it in simple terms, we write our computer program in a text file, and when we execute this program, it becomes a process, right? So when you're writing it, that's a program. You write a program, and when you execute it, that's a process which will perform all the tasks that we mentioned in the program. Okay, so that is why program is said to be a passive entity and process is said to be an active entity. When a program is loaded into the memory and it becomes a process, it can be divided into four sections. And what are these four sections? Stack, heap, text, and data. Right? In this figure, we can see the components of the process. The last block, there's written text. Just above is data, then heap, and then stack. So there are four components: text, data, heap, and stack. We shall be looking at one by one. Okay. So the text section, it is made up of compiled program code read in from non-volatile storage when the program is launched, right? So text section, it includes the current activity represented by the value of program counter and the contents of processor's registers, right? The data section. The data section is made up of global and static variables allocated and initialized prior to executing the main. Okay, so the data section has global and static variable that are allocated and has to be initialized before the program can start executing the main. Okay, next is heap. The heap is used for dynamic memory allocation and is managed via calls to new, delete, malloc, free, etc. The stack is used for local variables. Space on the stack is reserved for local variables when they are declared. Okay, so the four section text section will have the compiled program code that is supposed to be read. The data section, when it has global and static variables, right, that are supposed to be allocated and initialized prior to executing the main. The heap will be used for the dynamic memory allocation, and stack will be used for the local variables. Okay. Now now next is process relationship. you know the process can be an independent relationship or a cooperating process, right? So independent process will not have any sort of a relationship, right? So what's an independent process? A process is independent if it cannot affect or be affected by other process executing in the system. Okay, so it has no sort of an interaction, I would say, or no sort of an communication with any other process. It is stand alone in itself. It doesn't require anything to be read from somewhere else. It doesn't require to anything to be mm, written into somewhere else. It is just independent. It just doesn't need any other process. So that's an independent process. It does not share any data with any other process, right? So it is self dependent. A process is cooperating if it can affect or be affected by the processes executing in the system. What's a cooperating process? Which is affected and which is affecting also. It is being affected as well as affecting other processes in the system. It shares data with other processes. Okay, so it will share data with all the other processes. So that's a cooperative process. Okay, and what are the reasons? Why does it need to cooperate? See, information sharing. This is very clear, right? So it needs to the communication will need some sort of an information sharing, to whatever extent it may be, a small extent or to a large extent, that is dependent upon the work that each of them does. But this is definitely one of the most important and primary need as to why processes communicate. Next is computational speed up. Okay, see, whenever you share data, so you are actually like you're transferring your work also to other processes, and like anybody can whenever you delegate your work to somebody else, you try to just speed up the process kind of stuff. So you actually delegate it to various kind of stuffs, and you try to speed up and you enhance your speed. Modularity. See, when you'll make processes to individual tasks, and when they'll communicate with each other and pass on the information, I can differently divide my programs into various variant modules and then execute them. My process can be divided into various modules, and then it adds modularity. So modularity is a very positive aspect. Next is convenience. So it makes my program very convenient, and it's really easier. Like if all the work is being put into one, so then it's very difficult. So it becomes convenient when you kind of carry out this process of cooperation. Okay. Next are the different states of process. See, there are various states of a process. In our diagram, how many we can see? New, ready, running, terminated, and in the last is waiting. Right? So there are five different, one, two, three, four, five different process states that I can see in the diagram. Right? And there are various arrows going in from one to the other. Saying new means something new will be like the name is suggesting. You can guess something from the name also in the diagram. So new, then from new it's admitted to ready, then from ready it is going to running, it's exiting by terminated, from running it is coming back to ready by an interrupt, from running it's coming to waiting by input output event, from input output it's going to event completion, then from ready to running it's going by scheduler dispatch. So some information you can actually see it from the figure, right? Now we look as to how exactly it's like what's the exact function. So we look at it one by one. Okay, So we have five different states, right? What's the first state? Mm-hmm. It's the new state. The process is in the state of being created, right? The process is about to be created but not yet created. Okay, so it is being created, it is about to be created, but it has not yet been created. It is the program which is present in secondary memory that will be picked up by an OS to create the process. See, this is a very kind of a, like, you need to see the very minute difference. It is not being created, but it is about to be created. That's why it is new. Anything which has already been created is not new, na? So anything which is about to be created is new, right? So it is being created. It's in the process of being created. And the process is about to be created, right? Not yet created. Okay. Next is the ready state. After the creation of the process enters the ready state. What is the ready state? That is, the process is loaded into the main memory. So after you create the process, once it is created, so you will enter the ready state. That is, you load it into the main memory and you're not taking it for execution, but it is ready. It's just wasting for the CPU time, that it can get the CPU and it can start executing its instructions, right? So processes that are ready for execution by the CPU, they are maintained for in a queue for ready processes. Okay, so there's a separate queue for it, which is known as which is doing the keeping all the ready processes in it, and it's maintaining them. Next is running. You know what is happening here is that the process is chosen by CPU for execution, and the instruction within the process are executed by any one of the available CPU cores. Okay, so this is where the actual work is being done. What is being done? The process is executing by the CPU. Okay, and it is doing work. How it is being executed? By following all the process instructions. Whatever is in the process, written in the process, the CPU will do that. Okay, if it says go and fetch this file from secondary memory, it will go and fetch the file from the secondary memory. If it says you write this, then it will start writing into that file. So whatever the instruction is in the program or the process, the CPU is working on that. So this is where the actual thing is happening. The waiting process. The process cannot run at the moment because it is waiting for some resource to become available or for some event to occur. For example, the process may be waiting for keyboard input, right? Suppose there is a program which says that it starts that enter the number of whose table you want to see on the screen, and it takes the user from the input. So this program has halted itself. Halted for what? To get a number from the user, right? So it is waiting for some event to occur, and right. For example, the process may be waiting for keyboard input. Just now we discussed the disk access request, inter-process messages, a timer to go off, or a child process to finish. Okay, so but it is waiting for any, you can say. And then again, after it will get this waiting, it will go to running. Okay, and the last is the terminated. That is, the program is finished execution and the process is being killed. So this is the last stage, the terminated stage. And what are the operations that are being done on this? What is the first operation? Creation. That is, once the process is created, it will be ready and come into the ready queue, right? So that is being created in the new stage, scheduling. Out of the many processes present in the ready queue, the operating system chooses one process and start executing it. Okay, so it will choose among all the processes and it'll see as to which one to execute, which one to schedule, right? Selecting the process which is to be executed is known as scheduling. After the, so what is, it has been written that it will be finally, scheduler will do as to whom to allocate the CPU, like whose turn it is go. It is time for you, for that process to go and get the CPU execution, right? So it will do the exact execution of the CPU. Next is the execution. Once the process is scheduled for the execution, the processor start executing it. The process may come to the blocked or wait state during the execution. Then in that case, the processor start executing the other processes, right? So now you understand now what's being happening. And deletion is once the process gets over, the operating system will kill the process, right? The context of process PCB will be deleted and the process get terminated by the operating system. And now we see what are the operations. The process was being created. Scheduling is when it will select, as to the scheduler will select that which whose process turn is to go and get the CPU, which will get the CPU, which process will get the CPU for for execution, right? Execution is wherein the processes start executing. So this execution, after execution, may go to deletion, like without going to the waiting state, or it may wait, or there may be some interrupts coming up, then will have to wait and again start executing, right? So if it is completed, then it is deleted and killed, right? But unless and until like it is being fully executed, the entire instructions are being executed, it will wait, because some interrupts may also come. No, there are things, interrupts come, or it is waiting for some sort of an input output operations in itself. So this is how it is being done. Okay, so now this is the one that is really telling you where and which way it is this. So the process state transitions, see first one is the running, then it's runnable in memory, runnable swap, sleeping in memory, sleeping swapped, right? So from runnable in memory, it's assigned the CPU and it goes to running. Then it is preempted. If it is preempted, it goes to runnable in memory. If it is sleeping, it will go sleep in memory. It wake up and again come to runnable memory, and again from there it will go to running. So from runnable memory, it can be runnable swapped, swapping being done, swap in sped, swap out, and from sleeping in memory, it can go to sleeping swapped, right? So from memory it can be swapped out also. Okay, so this is what the last two things are being doing, that from running it can come to memory, and from memory also it can go to the outside the memory also. So this is how the state transition is being done, by being assigned the CPU, preempting it, swapping in, swapping out, and the sleep thing. So you look at this diagram, and if you simply see, it's very very clear from there what is actually being done, right? So if it needs memory, then it had to be swapped out of the memory. So that is from runnable in memory, it comes to runnable swap. If it is in the memory, and then it has to be somebody else programming with the execution needs the memory, that it will swap out it from the memory, right? So we'll see how this is being done. An active process is normally in one of the 5 states in the diagram. The arrows show how the process changes state, right? So a process is running if the process is assigned to a CPU. Okay, a process is removed from the running state by the scheduler if a process with higher priority becomes runnable. So who will take out? The scheduler will take out. A process can be preempted if a process of equal priority is runnable when the original process consumes its entire time slice. Okay, a process isn't runnable in memory if the process is in primary memory and ready to run, but it is not assigned to the CPU. Okay, so it is ready to run. A process is sleep in memory if the process is in primary memory but is waiting for a specific event before continuing execution. Example, a process sleeps while waiting for an input output operation to complete, for a logged resource to be unlocked, and for a timer to expire. So when the event occurs, it will again wake up and is again sent to the process. If the reason for its sleep is gone, the process becomes runnable. Right? When the process address space has been written to secondary memory and the process is not waiting for a specific event, the process is runnable and swapped. If a process is waiting for a specific event and has had its whole address space written to the back to the secondary memory, the process is sleeping and swapped. So it is waiting. So the difference between the sleeping and this runnable is this: if it is waiting, then it is into the sleeping ones, and if it is not runnable, then it is into the runnable one, right? So that's the difference between the two. And if somebody else is requiring memory, then it will come out of the memory. So this is what is happening over here. If a machine does not have enough primary memory to hold all its active processes, that machine must page or swap some address space to secondary memory. So this is being done. When the system is short of primary memory, the system writes individual pages of some processes to secondary memory but leave those processes runnable. When the running process accesses those pages, the process leaves while the pages are read back into the primary memory. When the system encounters a more serious shortage of primary memory, what it does is the system writes all the pages of some process to secondary memory. The system marks all pages that have been written to secondary memory as swapped. Such process can only be scheduled when the system scheduler demands select these processes to be read back into memory. Right? Both paging and swapping, these are the ones that are used for being swiping in and swiping out and doing all these of kind of allocation sort of stuffs. So both this paging, and we'll be discussing it in our further lectures. So for the time being, you can just see to it that both the paging and swapping, it goes delay when a process is ready to run again. So for processes that have strict timing requirement, this delay can be unacceptable. To avoid swapping delays, a real-time processes are never swapped, though part of such process can be paged. A program can, right? So how much memory can be locked is limited by how much memory is configured. Locking too much can cause intolerable delays to processes that do not have their text and data logged into memory. Right, so trade-off between performance of real-time processes and the performance of other processes depend on local needs. On some system, process locking might be required to guarantee the system real-time response. So paging and swapping, this you'll get this clear into our next lectures as we'll be studying more. For the right, for the meantime, you can just kind of remember this in your mind. So hope it's clear. The important questions are: what's a process? What is the difference between process and program? This you should know also because it comes in Viva also, and you should. This is a very kind of question that is being very much asked, and you need to have a clear understanding of it. What are the contents of a process? What is process relationship? What are different process states? Write different operations on process and explain process state transitions. So we come to the end of this lecture. I hope you liked it. Thank you.